So in this video we are going to talk about three different kinds of learning rate schedulers. We will talk about the step scheduler, the reduce on plateau scheduler, and cosine annealing. So let's get started and see how these learning rate schedulers work in practice.
Before we apply the schedulers, let us establish a baseline. So here we are running the code without a scheduler, and then we will add the different learning rate schedulers to see if they improve the results. And this is also what I recommend in practice. First, running the code without the scheduler, and then adding the scheduler to see if it improves things. So here this baseline code is based on the previous coding video, where we have the multilayer perceptron and the lightning model. And yeah, we are initializing the multilayer perceptron, feed it to the lightning model, train 400 epochs, and then just look at the results. So let's do that and see how the results look like. Okay, let's take a look at the results. So here, this would be our performance baseline where we don't use a scheduler. We can see the model trains quite well, except that it of course suffers from overfitting, but this will be addressed in a different lecture. So here, let's consider this as a baseline and now add the different learning rate schedulers. So for this, I'm going to make 3 copies of this notebook, where in each notebook we are adding a different type of learning rate scheduler. So let me do that. So we are going to look at 3 different types of learning rate schedulers: a step scheduler, on plateau scheduler, and a cosine learning rate scheduler. We will see what those things mean in detail when we get to that notebook. But let's get started with a step scheduler here. So for this, we are going to modify the lightning model. So instead of importing it here, I will actually put the code from our shared utilities file directly into this notebook. And I also will need 2 imports, the torch metrics import and the torch functional import. Then the main modification here will be in the configure optimizers method. So now we are going to add the scheduler here. So we will define a scheduler from torch optim, and we are going to use the learning rate step scheduler. So here, the learning rate step scheduler will take as input the optimizer, because the optimizer is what has the learning rate, or what uses the learning rate. So we want to reduce the learning rate of that optimizer. And then we also have hyperparameters like the step size here and the gamma. So step size here means epochs in this context. So that means every 10 epochs we are multiplying the learning rate by 0.5, which essentially means we are reducing the learning rate by a half every 10 epochs. So this is the modification here we have to make to the configure optimizers, and then we also of course have to return the optimizer and the scheduler. And then we also have to modify the return statement here. So we are returning now the optimizer and the scheduler, of course. And we are using Python lists because in certain specific contexts, we sometimes want to return multiple optimizers or multiple schedulers. So the method here expects that we are returning Python lists for the optimizers and schedulers. But that's the only modification we have to make. Now we can run the code and can see how the scheduler affects the results. So let's now take a peek at the results. As we can see, the validation set loss now converges. So this is a consequence of reducing the learning rate until it becomes, for instance, 0. So here we can also see the same thing happening for the training accuracy and the validation set accuracy. Notice that the loss here of the training set is always a bit noisy, and that is because it's computed on a batch by batch basis. Whereas for the training accuracy and validation set accuracy, these are more stable because they refer to the whole, basically, data set. Now it might be actually interesting to also look at the test set accuracy, and as we can see, the results are much improved compared to before, where we have 86% accuracy. We are now at 89% accuracy, which is quite nice. So it might also be interesting to take a look at what happens with the learning rate over the course of the training. So let's also do a dry run here, where I use the same step scheduler that we used above. And then we are manually iterating over the epochs and apply this update to the optimizer, so that the learning rate is reduced every 10 epochs here. So let's see how that looks like in terms of the learning rate. So we can see we start out with the initial learning rate of 0.1, and then every 10 epochs it's reduced by half until it converges to 0 here. All right, let's now take a look at the reduce on plateau scheduler. So we are going to use the code from the step scheduler as a starting point. And we saw before that we modified the configure optimizers method here. So now we are going to modify it a step further to use the reduce on plateau method or class. So let's use that one, reduce LR on plateau. And here we are again feeding the optimizer, but now we have different hyperparameters. One of those is the patience. So here, for instance, the patience means that every so and so many epochs, if there's no improvement in the loss, we will reduce the learning rate. And we will reduce the learning rate using a factor of 0.1. So this means we are multiplying the learning rate by 0.1. We reduce it to 10% of its original value if we don't see an improvement within 5 epochs. And for that, we also want to specify the mode. This is analogous to when we used the checkpointing, where we said we want to save the best model. If we use the validation set accuracy as a metric to track, we want to say max. If we want to track the, for example, training loss, we can set that to min, because the lower the loss, the better. Now, optionally, instead of returning things like this, we can also return a dictionary with more, let's say, detailed configurations. And I will share a documentation file with you where you can read more about that. So let's replace the return statement with this dictionary that I mentioned. So here we have now an optimizer that we return like before, and our scheduler here. And in addition, we can say what we want to monitor, here in this case, the training loss, and we can also specify the interval, for example, here epoch. We can set it to step, and then if we set it to step, it will modify the learning rate every batch, basically, instead of every epoch. But we will keep epoch here, and then the frequency means every epoch it's monitoring it. And let's apply this and see how it works. So we're going to run the code now, and then we can compare it to before. Okay, time to look at the results. And as we can see, again, at some point the loss saturates, it converges to a fixed value here. So similar to the step scheduler. Based on the results, we get pretty good results here, 89.5% accuracy. All right, let's now talk about cosine schedulers. Cosine schedulers are among the most popular learning rate schedulers out there right now, so that's going to be an interesting one. And there are also different flavors of cosine scheduling, so I will show you a brief overview before we apply actually our code. So the first type of cosine scheduler is cosine annealing with restarts. So with this particular scheduler, we are restarting the learning rate every so many epochs. So let me visualize how that looks like so that you can get a feeling for it. So here we have the cosine annealing learning rate scheduler. We feed it again the optimizer, and we have this tmax argument now. So this means that every so many epochs we are restarting the learning rate, and here it's the number of epochs divided by 10. So here it will restart the learning rate every 10 epochs. And the code below is similar to what I used before, where we just manually apply the step here to visualize or simulate the learning rate scheduling. So when we plot this, we can see, every 10 epochs, it's restarting the learning rate here. So this is one way we can use a cosine learning rate scheduler. However, in practice, it's actually more popular to not restart the learning rate, but to decay with a cosine schedule over the whole course of training. So I will show you now cosine annealing with a one cycle schedule where we decay it every epoch. So how does that work? So what we are doing now is we are setting just tmax to number of epochs. The rest here is the same as above. And then let's take a look at how that looks like. So here we can now see we are using a cosine schedule to reduce the learning rate for the whole course of the training for the 100 epochs here. Now let's talk about cosine annealing with a one cycle schedule where it's the same as above, except now we are decaying for each mini batch. And this is even more popular than the learning rate schedule we see here above. It's essentially a modification where we, instead of decaying each epoch, we decay each mini batch. And here's the code for that. It's essentially the similar code for the cosine annealing learning rate, except now that we have, instead of the number of epochs divided by 10 for Tmax, we now have number of steps here. And the number of steps is computed by multiplying the number of epochs with the number of mini batches. So for example, if we have 100 epochs, then we multiply this by the number of mini batches to get the total number of steps. And this will then be used to decay the learning rate for each mini batch. So below here, the code, it looks a bit, let's say, complicated, but it's just a second x-axis on the matplotlib plot that I added here for visualization purposes. So this is not really relevant. So let's take a look at the plot to get a better feeling of how this looks like. And as you can see, now we have the number of iterations here. However, if we would take a look at the epochs, it's exactly the same beginning and end in the same curve here, except now we are modifying the learning rate each mini batch instead of each epoch, but essentially it's the same concept here. Now in practice, people also like to use warm starting in cosine annealing. So since we already covered a lot of information in this video here, we are not going to talk about warm starting here in this video, but I will design an exercise where you get to practice or get to experiment with warm starting later on. All right, let's now modify the lightning model to use the cosine annealing learning rate scheduler here. So what we are going to do here is to replace the reduce LR on Plateau with cosine annealing learning rate scheduler. We are keeping the optimizer here, but we are now changing the hyperparameters, of course. So now we are using the Tmax, of course, and let's set that to self.cosine Tmax. So we have an attribute self here, self cosine Tmax. So that means that we have to pass this one also to the constructor and define the attribute up here. So let's quickly do that. So this should be a attribute, a class attribute. And then of course, since we want to modify it every batch and not every epoch, we also have to change it here to step. This will cause the learning rate to update each step instead of, or each batch instead of each epoch. So other than that, the only modification we also have to make here is, of course, to also define the number of steps. So we do that here. We define this at the top of this notebook, and this should be all we need to do in order to apply the cosine annealing. So let's run this code and see how it looks like. All right, let's now also take a quick peek at the results. And as we can see, the losses also converge here, which looks good. And the same is true for the accuracies here. Yeah, we still have that overfitting, but like I mentioned, this will be addressed in a separate lecture. Yeah, and lastly, let's take a look at the test accuracy. So here, 88.5%, that looks also good to me.
Yeah, so in this video, we learned about 3 different types of learning rate scheduler. We learned about the step scheduler, the reduce on Plateau scheduler, and cosine annealing. We saw that learning rate schedulers can improve the results compared to using no learning rate scheduler. However, they come with additional complexity, so it's always a good idea to have a code example without a scheduler as a baseline. With that being said, which learning rate scheduler you use is also yet another hyperparameter. In practice, I also recommend comparing different types of learning rate schedulers to see which one works well on your problem task.